Okay, welcome Organic Chemistry 2342, Organic Chemistry 2. We're going to continue on this week with chapters 14 and 15. So we're going to look at benzene and other aromatic compounds and how they relate to our chemistry. So as you've all seen, we have our new Zoom meeting room, which is right here. It has that new number. Remember, that's new each week. It comes out on the email each week, okay? So our homework is open and available to you on Top Hat for chapters 14 and 15. Again, it's due Thursday night at midnight. And then after that, you can use it to review. You can go and review the questions you got and the questions you got wrong and go ahead and use that as a study guide. We'll have our second group project on Thursday on the second half of the class from 1 to 140. It's going to involve multi-step synthesis of benzene rings. And so you'll have to figure out which way to go to, which reagents you get to use first because of direction and deactivation. So we're going to have to work with that back and forth. So that's why I really want to do that before the exam, because it gives you some practice on the knowing which way to go, which synthetic route is going to give you the desired product, okay? Our second exam will be on Friday on chapters 14 and 15. It'll be approximately 30 questions, 30 to 35 questions again. It'll again start online at noon, okay? The Procterio is set up slightly differently. You will have to show ID and you will have to show your blank paper. Because it's set to a slightly higher level because of that, you might get kicked out, and that's okay. I'm going to monitor it and I'll be able to get you back in. So let's go ahead and just so you're warned that you will have to have a picture ID. It can be your school ID or driver's license, and you'll have to show your blank paper. And then so it's not going to like shout at you or anything like Examity, but it's going to be a little different. And so unfortunately, I also have a meeting scheduled this Friday, so I can't have my half-hour happy hour. I'm hoping to have one eventually, so we'll get to that soon. Okay, so that is all the administration for this week. Test corrections. That's a really good question. I need to talk to the guys at Top Hat to figure out if you can review it and then in a secure way so they don't like put the answers up on to something like CHEM. That's why we're doing it this way, because of so many of us are having to take tests online. We just don't want the answers to show up on CHEM. I'm asking them if we can do that in a secure way. And but right now, if you set up an email Zoom meeting with me, I can go over the exam question by question and let you know which questions you got wrong or which questions you got right. Okay? Does that answer the question? All right, great. Okay, so let's go ahead and I'm going to try to share my screen and let's see if that's going to work for me today. It was working pretty good this morning, so let's. Okay, it looks like it might be working for me. There we go. All right. So these are the slides that, of course, are on Canvas and on tracks. This is the full set of. This is what I call the. Did you see my text message? The computer charger and the video slides. So these are the ones that are empty. Yeah. If you want, my computer shut up. Let's go ahead. Let's see, we got, all right. There we go. So, can everybody hear me still? Yeah, okay, good. Had some noise in the background there, so I muted. Okay, so what we're going to do is we're going to go over these. Again, if you're looking for spelling, you might not be able to read my spelling and stuff like that. Those are on the full slides that are online, and they're also in your book, specifically the spelling for the special benzenes that we'll have to remember. Those are in your book on, I believe, in chapter 14. So there's a whole page of those special spellings. So. Okay, so let's move along and get started on our chapter 14, benzene and aromatic compounds. Okay, so in the early days of chemistry, they started classifying things by, oh, it's a hydrocarbon, it's not a hydrocarbon. And then they started classifying things by, degrees of unsaturation. So if you have a fully saturated hydrocarbon, you have as many hydrogens on as you can. Once you got 1 degree of unsaturation, that gave us an alkene. And that way we could see that unsaturation by the way it reacted. It reacted differently than saturated hydrocarbons. Okay, and so then you also get a degree of unsaturation when something's in a ring. Okay, so you might want to go back and remember what degrees of saturation was. That's in the first half of the book. It was introduced in the alkene chapter, I believe chapter 6, so that you can go and review that. But when they started looking at benzene and how it reacts, they figure out it didn't react the way that alkenes react. Okay, for example, if you have an alkene and you, like just old ethylene right here, and you react it with bromine, right, you get an addition of bromine across that double bond, okay? And so they said, well, this is an unsaturated compound too. Let's do that same reaction, and nothing happens. So when they reacted benzene with bromine, even with heat and everything, different solvents, nothing happened. It didn't react. So there had to be something different about it, okay? So in our benzene ring, we figured out that it was unsaturated, 1 for the ring and 1 for each of the double bonds. So it has 4 degrees of unsaturation, okay? And we noted it's a ring and it has 6 members in it. And so we have to think about, ooh, there's a possibility of resonance. We have an alternating double and single bond, so we should be able to show resonance contributors and look at what the resonance hybrid might be. So if we look at just benzene by itself, we're thinking, okay, so our first resonance structure is going to be where the double bonds are in this position. And then, of course, because in a resonance structure, we're only moving electrons. If we flip those electrons and we move them somewhere else to the opposite direction right here, that would give us our 2 resonance structures. Remember, our resonance structures here are not the true thing. Somewhere in between is the actual structure. So when we draw our resonance hybrid for benzene, we can draw it as a dashed line going in between all these different little, these 6 bonds right here. Or a lot of times we'll actually draw it with a circle in the middle. That's indicating you have delocalized electrons around that entire ring. And so it's very common to see a benzene ring with that circle in the middle. In fact, I'm probably going to almost exclusively do that, except when we're actually doing mechanisms where we want to see where the electrons are coming from in the system. So we'll start to see that, okay? So another way to represent benzene is to think about it as, okay, we have this pi cloud above and below the ring. So the actual carbons in the benzene ring are sp2 hybridized, which makes them trivial and planar. So they're trying to be 120 degrees apart. And that's why we have this nice flat ring and all the angles are 120 degrees. But when it's sp2 hybridized, that means we have a p orbital that's unhybridized, okay? So if we have those p orbitals that are unhybridized sticking above and below the plane, they start to blend together, because just like in other kinds of the extended conjugation we saw in the butadiene system here, they're planar. They are all of the same energy. And so we end up getting this cloud of electrons above the plane of the atoms and a cloud of electrons below. And that's why sometimes it's represented as this circle right here, because it is that all those electrons are just moving around and around and around. Okay, so we have this sp2 hybridized carbon, and we have confidence that our hybrid structure is correct, because when we look at the bond lengths in a benzene ring, we see that, number one, no matter how cold we make this ring, the bond lengths are all the same. All the carbons have exactly the same carbon-carbon bond length, okay? And that bond length is halfway in between what it would be for a regular alkene, like this this ethane right here, and this fully saturated hydrocarbon here, the ethane, Okay, so between ethene and ethane, that means that that bond is somewhere in between. So it's got a little bit of partial double charge, a little bit of partial single charge, and therefore it gives us that intermediate bond length. Okay, and that resonance stability, that possibility of spreading the electrons out, gives us our reactivity and our stability. Okay. So let's start naming these things, okay? So whenever you have just a simple alkyl group on it, you want to name it for whatever the group is and add the word benzene. So it's nice and easy. So if you had an ethyl group on here, that would make it ethyl benzene. All one word, no space, no hyphens or anything like that. And so if you have the T-butyl group on there or the tert-butyl group there, it'd be tert-butyl benzene. And if you have a group on it that does not change the name, and we'll talk about that in the next slide, then you just add whatever that group is and the word benzene. So in the case of this would be bromobenzene. And then chlorobenzene or nitrobenzene, okay? So it's fairly simple to name things when they have one thing on them, okay? However, there are a large number of these that are so commonly used that they have different names. The functional group changes the name of the benzene ring. And so we do have to memorize these because they're going to be used in our nomenclature, and they have certain specific names. And they started out in the chemical industry as changing the names based on kind of how they reacted. So in the case of this methyl group here, it's the only alkyl group that changes the name of the benzene. So is a methyl group. And when you have one of them on there, it's called toluene, right there. And so one methyl group is toluene. And so you can actually have like bromotoluene, chlorotoluene, and we'll have things like that. If you have an OH on here, that's an alcohol group. So you start thinking, oh, it might be like an alcohol, and it is. It's the phenyl group with an alcohol on it, so we call it phenol. So NOL, just like any other alcohol, but phenyl group, so phenol, okay? So this is an amine right here, so we're gonna have to change the name into aniline, A-N, aniline here. So it's starting with an amine group, so right there. This one right here, this is a sulfonic acid group. And so we call this benzene sulfonic acid. All one word. I'm having to hyphenate it because I have to bring it down here. Acid, okay. Now, when we have this methyl ether group on here that we see on the next thing right here, that's another compound, and it has a really high reactivity to a lot of substitution reactions, but it has a new name. It's called anisole. Right here. Now, this can be called phenylethene, which would be kind of hard to do it, or vinyl benzene, but it actually has a name that's called styrene. Styrene. And that's, yes, with a Y in it right there. And you may hear this name a lot, polystyrene. Polystyrene is actually made out of styrene. So it's easy to remember that it's this vinyl benzene group here. Once we put an aldehyde on here, we have to call it benzaldehyde. So we have the full name is benzaldehyde. It's little b, benzaldehyde. And then when we have the carboxylic acid, we call it benzoic acid. So we start with our name benzene, drop the end, add oic acid, benzoic acid. And our last one right here is called benzonitrile, because that C triple bond N is sometimes called the nitrile group. And it's a carboxylic acid derivative, but we call it benzonitrile. Benzonitrile. It's all one word, but running out of space here. Okay, nitrile with an E at the end. Okay, and all these are spelled correctly in the book, so, and on the slides on Canvas, so don't be afraid to double check there. Okay, so those are monosubstituted benzenes, and they're fairly easy to name that way. Now, once you get to two substituents, now you have to start figuring out where they are and what position they have on the ring. So we have two methods for doing this. We have a numerical method that is always correct and is always used in IUPAC. And when you have 3 groups or 4 groups, you would also use a numerical name. However, we also have a different naming system, which is called the ortho-meta-para. Well, let's first talk about our number system here. And so if you have 2 groups that are the same, you assign one of them the number 1, and then the other one you're going to assign is the lowest number possible. Just in like you're naming an alkane chain or other things like that, you're trying to get the lowest possible number. So in the case of 2 bromines here, we're going to assign one of them the 1 position. And then if we go this way, we have the other bromine at the 3 position, okay? If we went the other way, it would end up in the 5 position, and that would be not the lowest number possible. So our number here is going to be 1, 2 dash dibromo, because there's 2 bromines, bromo benzene. Okay, so now if they're different groups, then all we do is put them in alphabetical order and put the lowest alphabetical number as number 1, and again try to get your lowest number possible. So in the case of this chloro-iodo compound, chloro would come first alphabetically. So it'd be 1 chloro and 1, 2, 3 iodo benzene. Okay. And likewise, we would name this one something like, let's see, bromine would come first. So it'd be 1 bromo, 3 nitrobenzene. And in the case of this compound here, we have ethyl and chloro. Chloro would come first. So it'd be 1 chloro, 4 ethyl benzene. Okay, so it's nice and systematic, fits into all of our other nomenclature rules. Okay, now the other method of naming them is unique to benzenes, and it's unique to di-substituted benzenes. Okay, so if you have 2 things attached to a benzene ring, you really only end up having 3 possible patterns available to you. Okay, and so what those would be what we call ortho, which is the 1, 2 is ortho, or the little o like this. The 1, 3 is meta, or an M, and the 1, 4 is para. And these will all be at the beginning of the name and have a dash on them. So you only really have 3 patterns, because by naming it the lowest number, 1, 2, 3, by the time you get to 4, that's the most you can separate 2 things, because then you're going to be 5 and 6 if you keep going around. So that's why we only have those 3 patterns available to us on di-substituted benzenes, okay? So we would, if they're the same name, you would name them ortho-dichlorobenzene, for example. This would be that. If we had them as different names, you would just put them in alphabetical order. And so this would be ortho-dichlorobenzene. Chlorobenzene. And if we had, let's just do our meta-chloronitro here, right here, we'd say meta-chloronitrobenzene.
Dr. Irvin?
Yes.
So the correct way to format it is to put the letter with a dash, or do you want us to write out ortho, meta, and para?
The letter with a dash is correct.
Okay, thank you.
You can write out ortho, but most of the time it's shorthanded to be the letter and a dash. And if you're typing, the letter should be italicized. But in writing, we don't notice the difference between italics and not. Okay, so while ortho, meta, and para are correct always, sometimes people just always use the numbers so that there's no worry about that. Okay. Okay, so going on with nomenclature of benzenes. Now, if you have a substituent that changes the name, for example, that methyl group on a benzene changes benzene into toluene, okay? If you have something that has changed that name, that becomes your number one position always, and all other substituents are based upon that. So for example, in this case here, we have a chlorotoluene, because the methyl group here turns it into toluene, and the methyl group is always in the number one. So to get us our shortest path to our substituent would be number 2. So that would be 2-chlorotoluene, or we could also say ortho-chlorotoluene, and both would be correct. Okay, in this step, in this group right here, we have an amine group which does change the name, and a nitro group which doesn't change the name. So in that case, we have what we would say was we name it for the amine group here, and that would be aniline. And that nitro group is in the 4 position. So we're going to call that 4-nitro aniline right here. And when we have our hydroxy group on our benzene ring, that changes it to phenol. And so this would be 2-ethyl phenol. Oh, there's no E at the end, sorry. Phenol, right here. Okay, so now we have one other rule we need to include here, is that if we have 2 groups that can change the name, you have to go with the name of the highest order thing, the highest priority. Okay, now if you go to Canvas or Tracks and look at that nomenclature review, it has a list of which things are higher priority. Okay, so in the case of this right here, amines are actually one of the lowest priority groups. Then there's alcohols and esters and ketones and aldehydes, and carboxylic acids are always the highest priority of naming group. So because of that, we're going to have to name it for the benzoic acid here, and then locate where that amine is. So this is going to be 4-amino, 4-amino benzoic acid. Okay. Now, if we were to name this in the ortho-para meta structure, we would name this para-amino benzoic acid. Okay. So para-amino benzoic acid, or PABA, as you may see it on many labels, it's one of the active ingredients in many, many sunscreens. It's para-amino benzoic acid because it absorbs UV light. Okay, so that's how we name things if they are di-substituted and one of the substituents has changed the base name, okay? So we do actually have another thing that changes the name. And it's sometimes when you have 2 groups that are on the same benzene ring, they can change your name, okay? So in the case of 2 methyl groups, we can, instead of being methyltoluene, we actually have changed the name to xylene, okay? Xylene. Okay, that's 2 methyl groups on the same benzene ring. And of course, we have 3 isomers of this. We have the ortho one, which would be orthoxylene, metaxylene, and paraxylene. And I'll draw the paraxylene over here, where the methyl groups are just in the 1,4 position, or opposite each other on the benzene ring. One of the other ones that is di-substituted, has a special name, is when you have toluene, but then you have an amino group on it too. So you got to mix together the words toluene and aniline together, and you end up with toluidine. Okay, so I'm going to draw a couple of the toluidines here. This is N2 and CH3. and the word is toluidine right here. And this particular one is the meta-toluidine, okay? And they, of course, can be in all other of the systems where it can be ortho, meta, and para, okay? So these are probably the more complicated of the self-named things, but xylenes have 2 methyl groups, toluidines have a methyl group and an amino group. Okay.
Are we ever gonna have to deal with 3 groups?
Yes, on the next slide even.
Oh, okay, great.
So, but those are the special names for disubstituted. Once you get past disubstituted, we have to name them systematically, okay? So when we go to our trisubstituted, by the way, thank you for the setup, we have to think about, number one, is the ring named for a substituent? If the ring is not named for the substituent, we just try to do the lowest number possible. So in the case of our first compound here, we have a nitro group, a bromine, and a chlorine. None of those change the name of the benzene ring. So all we have to do is figure out how to number them so that they're the lowest number, okay? So if we started here with the chlorine here and named it 1, 3, and 4, that's higher than if we started from the nitro group and did 1, 2, and 4. So that's why we're gonna name it with that lowest number set. After we figured out our lowest number set, then we just have to do them in alphabetical order. So we have chlorine, bromine, and nitro, which means the bromine is going to come first. So that's going to give us 2 bromo. Go ahead.
Does nitro not have priority over chlorine and?
But because the nitro does not change the name, it's not like an amine, which would change it to aniline. So the nitro group is just a substituent and did not change the name. Okay? So that's what I'm talking about priority.
Okay, so benzene is different from chains in that like if it doesn't change the parent name of the molecule, then there's no like priority, you know, like when you're naming a chain, like carboxylic acid has priority over alcohol.
Correct.
So okay.
Yeah, no, it actually follows the same rules because in this case, the benzene is the parent because it did not change names. It's not a toluene or an aniline. Therefore, just like in a long chain where we would say, okay, we have bromo, chloro, alcohol. So the alcohol is changing the name, but in the case of with the substituents that don't change the name, those are always in alphabetical order.
Oh, okay.
Always trying to number them at the lowest number possible. So it is following the rules.
All right, I get it. I understand. Thank you.
4 chloro and then 1 nitro benzene. Okay, so nitro, and there's a Z in here somewhere. All right, so we are using our same rules of put them in alphabetical order and put them in lowest number possible. So this other isomer here, because we've moved the substituents a little bit right here, we're still going to have it as, it's going to change the name to 4 bromo, 1 chloro, 2 nitro. So only the numbers change because none of them change the name of the benzene ring, okay? So, and then of course, this would be another isomer of the same 3 substituents. Okay, however, when we do change the name, we again always start with whatever substituent changed the name as position 1, and then still try to get to our lowest number. Let me show you an example of that on these ones right here. So in this case here, we have this methyl group right here, changing our name. So we know it has to be based on toluene, okay? So, and because this has to be our 1 and our toluene, we now have to figure out which direction to name it to get to the lowest number. So if we go in a counterclockwise position, we would have 1, 2, 3, 4, 5, 6 right here. But if we went in the clockwise direction from this 1 in this direction, we would have 1, 2, 3, 4, 5. Okay. So if we go in a clockwise direction, we have a lower numbers. Okay. So we know that the 1 is on the methyl group is changing the name to toluene. So we know the 1 is on toluene. So if we label it from in the clockwise position, and then again, we still have to do things in alphabetical order. So we'll start with, that turns us into 5 bromo, 2 nitro, and toluene right there. Okay, so if it changes the name, the thing that changes the name defines position number 1. Okay, so if we look at the next one here, this one right here, we have an OH here which changes the name to phenol. And we have this direction here is going to give us our 3 and our 4 position as our 2 lowest positions. So we now do it in alphabetical order. So we have 3 bromo, 4 chloro, phenol. Right there. Okay. So in an last example here, we have the same kind of situation. We have, let's see, I haven't used what. The amine group here is changing the name to aniline. And our lowest number system is going to be in this direction. We have ethyl versus iodo. So we're going to start with 2 ethyl, 4 iodo, aniline. Okay, and so you can, after you've gone past those 2 substituents, 3 and more, you always use those same rules to number it. So you can name 4, 5, and 6 times substituted benzene rings this way. Okay, so now we have a new rule that we haven't used before, is that we can think of the benzene ring as not the biggest part of the compound. For example, if you had a long hexyl chain that has 7 carbons, that's actually going to name the chain, and your benzene ring has to be a substituent. Okay, so when we have a benzene ring as a substituent, we actually call it the phenyl group. Okay, and we saw this before when we were naming alkenes. We had 2-phenyl propene, where we had it as a substituent because it wasn't named for the benzene ring, it's named as a substituent. And if it's attached to something here, we call that the phenyl group. Phenyl, that's an N, sorry. But if we have a benzene ring with a CH2, and then that's attached to something, that's called something else. That's called the benzyl group. Okay, that means if we have something like an ether, we had 2 benzene rings and they were hooked directly to an oxygen here, we would call that diphenyl ether. However, if we had 2 of these with that CH2 in between the oxygen here, that's a benzene ring there, trust me, that is the dibenzyl ether. Okay, so when we're using it as a substituent, and we cannot take it as our parent right here, so we'll use the name phenyl for directly bound to the benzene ring, and benzyl if you have a CH2 in between the benzene ring and whatever group it's attached to. Okay, now because toluene, the methyl group only, is the only one that changes the name, every other thing is changed to a name like this. So this would be our longest alkyl chain right here. So that is a propyl group. So we would actually name this 2-phenyl, or you can name this isopropyl benzene as a possibility, because it has, the straight chain has fewer than the the carbons in the benzene ring here. If we had this right here, we'd call that butyl benzene or 2-butyl benzene, because it's the benzene is attached to the 2 group in the thing here. This would be T-butyl benzene, because that's the tertiary butyl group. It's 3 methyl groups onto the same carbon, giving us a quaternary carbon. Now, once we get up to things like this right here, this is a chain of 5, okay? So that makes it a larger chain, a large chain. And so we actually are using the phenyl group as a substituent. We're going to call this 2-phenyl pentane. So we're locating the 2 is its place on the pentane chain right here. And if we move that phenyl group over 1 position, that would make it the 3-phenyl pentane. So pentane and anything above gets named for the alkyl chain, and the phenyl group is a substituent. For alkenes, anything 3 and above, and the phenyl group is a substituent. Okay. It's sometimes hard to get, but it is there. Okay, and the last thing I want to do is talk to you about in this section is that when we're talking about any kind of generalized term, for example, an ROH, R is for a saturated alkane, okay, or an sp2 alkane or an sp3 alkane. If we have an aromatic ring on there, we actually change it to AR and then whatever the substituent is. So in this case here, that means this substituent is bonded directly to the benzene ring, and that's the AR, okay? Now, one thing that's not on this slide, but it is in the book, is that if you have a something bonded to a benzyl group, so where you had a CH2OH, that's called the BZ as the generalized term for the benzyl group, okay? So R means alkanes and alkenes, AR means a benzene ring or a phenyl group, and the benzyl, BZ, stands for the benzyl group, that benzene with a CH2 in between that and whatever functional group you have. Okay, so that brings us to the end of part 1 of chapter 14. Okay, I will answer questions now, and then we can also move on to part 2 after that. Any questions right away?
So for the benzyl group, the only thing that makes it different is that you're going to have a sp2 hybridized carbon hanging off the side, or sp3. Sorry. Yeah.
Yes, you have to have that. You have to have that CH2 in between.
Okay.
Yeah, that changes its reactivity, and therefore it changes its name.
Okay. Thank you.
Hey, Dr. Irvin. For the, I noticed you mentioned the saturation, degrees of unsaturation at the beginning of this chapter. Is that a concept that's going to be explored more heavily? Should we go back and like brush up on that if we're not too familiar with it?
Just knowing what degrees of unsaturation is and how to calculate them will be talked about a couple more times throughout the semester. So you should brush up on it just a little bit.
Yes, sir. Thank you.
Okay, so now let's talk about benzene, its reactivity, and aromaticity, okay? Okay, the BZ stands for the benzyl group. The benzyl group is a phenyl group with a CH2 and then attached to something else. So in the case of, for example, this right here, the benzyl group is listed here. Right here is this right here. So we can generalize it as a BZ something else, benzyl group. Okay, does that answer your question? Okay, so let's move on to aromaticity and what it means, okay? So one of the things we need to remember is that this is an sp2 hybridized carbon bonded to other sp2 hybridized carbons, and we have that pi cloud above and below the plane created by all of those sp2 hybridized carbons, okay? And when they first started studying these alkanes, and they were looking at it and saying, oh, you know, our degree of unsaturation was based on how many equivalents of hydrogen you could add to the system, okay? So in the case of cyclohexene, when they measured how much heat it gave out during this hydrogenation here, they figured out that it would generate approximately 120 kilojoules per mole of heat when they hydrogenated that, okay? So in theory, if you had two alkenes on the same structure, it should take twice as much, it should give off twice as much energy, because each of those alkenes would be isolated and would give off that much heat. However, as we learned about in the last chapter, conjugation changes that stability. And so if we have two alkenes on there, instead of being the theoretical 240 kilojoules, which is its theory, right here, when they actually measure it, they measure it to be 232 kilojoules per mole, okay? So what does that mean? That means just having those two alkenes in conjugation with each other stabilizes the system. It gives out less heat than it would have if they were isolated, okay? So if we extend that concept of, okay, having them in conjugation stabilized the system and made it have give off less heat, does that work with benzene? Okay, so in the case of benzene, we have a total of 3 alkenes. So in theory, we should have 360 kilojoules of heat being given out when we hydrogenate this, okay? So in theory, it's 360 because it's 3 times the 120. However, when we actually measure it, we see that we get 208 kilojoules per mole of heat lost, okay? What does that mean? It means that when we have those 3 in conjugation and we've delocalized those pi electrons over the system, we've actually gained about 152 kilojoules per mole of energy. It is that much more stable than just having the isolated alkenes by themselves, okay? So if there's energy that keeps that in there, that means that when in our reactions we're looking at, and we're going to be seeing in the next chapter, the return to that aromaticity is going to be a driving force we see, okay? So, and we call that, that difference in energy our resonance energy. That's the difference between the energy released from isolated systems and the energy related on the system we have. Let's see if I can help that. Let me switch over to a different Wi-Fi, see if I can't get my sound to come up better. Okay, let's try that. Is the internet connection is unstable now? Okay. How is the sound now? Is it better or worse?
It does sound better. I'm sorry, could you please go back over the concept of doing benzene to cyclohexane?
Okay.
That wasn't quite clear.
Okay, so what I wanted to show you here is through an experimentation, we can prove that benzene having its delocalized electrons in a ring is more stable than having isolated double bonds. Okay, so if we looked at the heat given off by just hydrogenating the cyclohexene with just one double bond in it, we see that it gives off 120 kilojoules per mole, okay? So if we had a cyclohexane with 2 alkenes in it, in theory, it should be twice as much heat given off during that hydrogenation. If that But when we measure that, we actually find that it's less than that. And that comes from the fact that those two double bonds are in conjugation with each other, okay? So that's the conjugation stability. In the case of benzene, it's actually much less heat given off during the system. And that difference between the theoretical of 3 isolated double bonds and the number we actually measure is this 152 kilojoules per mole, okay? What that's telling us is that benzene has a significant amount of energy stored in it because of, stabilizes it because of it being in that bond, having that resonance, having that aromaticity. So basically the energy is the resonance energy. And that's the difference between what would have been released if they were isolated double bonds versus what we actually get when we measure the hydrogenation. Does that answer your question?
Yes, sir. Much better. Thank you.
Okay.
I have a question.
Yes.
So we say that benzene is really stable because all of the 3 double bonds are in conjugation. So when we say that it's more stable, that means that it has less energy, like in the molecule itself?
It will give off less. It's more stable so that when you break it apart, it actually gives off less energy than if you had them isolated. So having those 3 in a conjugation, alternating back and forth. Remember, they're not true double bonds. They're half single bonds, half double bonds, and they're constantly moving, right?
Mm-hmm.
So that constant moving is stabilizing the system, and so it wants to stay in that lower energy state.
So does that mean that it takes more energy to convert it from benzene to cyclohexane?
It does not give off as much heat when you do that, yes. Hydrogenation typically gives off heat.
Okay. Okay. I think I'm focused too much on like the concept, like the conceptual. But
What I really want you to understand is that aromaticity actually is an energy saving force, and therefore it wants to return to aromaticity if at all possible.
okay.
Okay? Now, because of this, we're actually getting different reactivity than if we had those isolated double bonds, okay? Okay. Now, because the hydrogenation didn't give off as much heat as we predicted, that means that there's something else going and driving this force. And that is what we consider our stabilization by having it become aromatic. Uh-oh, I'm not sharing anymore. I'm gonna stop sharing and reshare. My screen did not change. Oh, wrong one. Come on. Let me see. Come on. There we go. Okay. Okay. So what I really want you to know is that, that hydrogenation did not give off as much heat as it should have, meaning there's some other thing giving us stability here. Okay. And that these typical reactions of other alkenes don't work on don't work on benzene. So for example, if we had benzene right here and we wanted to react it like it was an alkene, like one of those reactions we would use is just, let's add bromine across that alkene, right? Well, if we do that with benzene and just do bromine and heat, no reaction, okay? And if we wanted to take it and let's say we wanted to oxidize it as if it was an alkene, you can oxidize your alkene down to a carboxylic acid using something like potassium permanganate. Okay, again, no reaction, no oxidation reaction right there. And if we took our alkene and we took acid and added water to it, right, we would get an addition across that double bond and give us an alcohol. Well, in benzene, no reaction, okay? And even a hydrogenation reaction that typically works very quickly with isolated double bonds, with something like nickel and hydrogen here, it reacts very slowly. Okay, so the fact that these reactions don't work the exact same way means that there is something else happening here. And one of the first things that was noticed was, instead of having this bromine add across the double bond, if you added the correct catalyst, instead of getting addition where it would lose some of your double bonds, if you added bromine and a Lewis acid catalyst, and we'll talk about those in a minute, you actually get substitution reactions where you get one of the bromines ends up on the ring and the other one is kicked out with the hydrogen that used to be on the ring, okay? So benzene doesn't like to undergo addition reactions, but it does do substitution reactions, okay? Now, why? Okay, and that has everything to do with the idea that we have a stabilized system, and in this particular system, that stability is much higher than just conjugated dienes. So we have a new term to talk about, and what we're calling that is aromaticity. Okay, so aromaticity originally came from the idea that a lot of these compounds like toluene and other things had a different smell than just regular double bonded systems. And so they were called, oh, those are the more smelly ones, or they are the more aromatic systems. And so we ended up getting that whole set of compounds named because of their unusual smells, okay? But to get this extra stability, we have to follow 4 rules, okay? Now, the rules of aromaticity are the molecule must be cyclic. We're going to start with just single rings right now, but we're going to extend that to multiple rings. So it just has to be cyclic, okay? Number 2 is you have to have uninterrupted p orbitals, okay? There has to be an available p orbital on each and every atom in the ring. It can have an electron in it. It can be empty, or it can have 2 electrons in it, but it has to have a p orbital, okay? The molecule must be planar. The reason it has to be planar is those p orbitals have to line up together so that they can share equally all the electrons available to it. And the pi cloud must contain an odd number of pairs of electrons, okay? And so we actually have a set of numbers that we're going to look for when we do this. It's an odd number of pairs, okay? So we're going to look for 1 pair, 3 pair, 5 pair, etc. Okay? And so what that gives us is a nice little way to calculate this is what we call the Huckel rule. And so the Huckel rule is 4n plus 2, okay? Now, n can be any number from 0 to 100, okay? We rarely get to that high, but it is any number from 0 to 100. So in the case of n equals 0, that gives us the number 2, okay? So that's 1 pair of electrons, right? 2 electrons is 1 pair of electrons, so that's 1. Then if we add the number 1 to this here, we're gonna get 6 electrons, which is 3 pairs of electrons. And if we added the number 2 here, that's 4 plus 2, that's 10 electrons. That's 5 pairs of electrons. Okay, so it's always odd numbers of pairs of electrons. So the numbers we're looking for in the electrons we're looking at are 2, 6, 10, and 14 and 18. Again, as we get to multiple rings, we'll start to see those numbers get higher and higher, okay? So this is just a way of accounting for the idea that we're gonna have 2, 6, 10, 14 electrons, and we're gonna look for that system, okay? All right, we're right here about 1 o'clock. So what I wanna do is I wanna stop recording, go ahead and pick this up in about 10 minutes, and everybody go ahead and have a break. And then I'll start posting this up when it can. And let's come on back here at, let's say, 1:05, and then, so that's only about 7 minutes. So 1:05, we'll come back and do this, pick up right here. Okay, so I'm going to stop recording.